This is not going to be a full lesson on how to simplify and rationalize radicals. This is going to be a quick reminder. There's other ways to do this. Probably in Algebra 1 you learn to do this making a factor tree, but we're not going to mess around with that in this class. That is way too slow. The way I like to do this is I like to try and split it up into two roots. I usually wouldn't write this step down, but I'd look at 40 and I'd ask the question, what's the biggest perfect square you can think of that goes into 40? You guys know your perfect squares, right? Those are the things we know square roots of. 4, 9, 16, 25, 36, and so on. So what's the biggest of those numbers that goes into 40? 4. And what would you multiply a root 4 by to get root 40? 10. So when I look at this, I think of this, I don't write this step down. I say, oh, that's just the square root of 4 times the square root of 10. And the square root of 4 is 2. So it's 10 root 2. Okay, you do not need to show me any steps for these in this class. I insist on it when I teach this in geometry. I'm not sure if they asked you to show those steps last year in Algebra 2 or not, but in my class you do not. So if you can do root 40 in your head and go, that's 4 times 10 and the square root of 4 is 2, so 2 root 10, that's fine. Just write down the answer. If it helps you to show a step, show a step. I'll do one more with you and then I'll let you guys finish up the rest of these on your own. 2 root 45, that's 2, and I'm thinking square root of something, what goes into 45? 9 goes into 45. 9 times 5. So let's see, that 2 is going to stay. The square root of 9 is 3. Don't know the square root of 5. Final answer is 6 root 5. All right, you guys do the rest here. Just up to here. Don't do the next part yet because I want to show you a little trick for that. $486. Goes into 486. 16? No. Does 4 even go into it? No. Oh, I need an odd number. It's 9. 9 does. 54 also has a 9 in it, so that makes me think there's something bigger. 81. Ah, there we go. 81. 81, that's square root of 81 times square root of 6. It's 9 root 6. We're going to be dealing a lot with radicals in this chapter, so this is one of those things that if you're not quite there yet, please get my help. Oh, I promised you guys a little quiz. You want to do a practice? And do a quick practice of our quiz. We're not going to take it today. Quick practice. We'll do it next time. We'll do it next time. Here, quick practice. Draw yourself two 30, 60, 90 triangles. I'm just doing this on the page that had all our wheels of fun from last time. And underneath that, draw yourself two 45, 45, 90 triangles. And don't put anything else on them for right now. All right, and copy down some ones for me. You guys have those drawn? Don't put anything else on here, okay? Don't put anything else on here. Put a 1 there, and there, and there, and there. Now these triangles might be spun around, and in some of those 30, 60, 90 triangles, it might just have the 60 or just have the 30, but y'all can figure out the rest of those. The ones will be given, and then you got to fill in the rest, okay? You ready? We got 30 seconds. On your marks, get set, go. Fill in the rest of the sides. Go, 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 go. Fill them in, fill them in, fill them in. Go, 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 go. $20 seconds remaining. $10 seconds remaining. 5, 4, 3, 2, 1. Time! Did you get it? Did you get there? Did you get them? Got all of it wrong? Well, that's okay, because the thing is, it's all or nothing. So either you get a 10 out of 10 or a 0 out of 10. All right, are we good? How many people got a 10 out of 10 on it? Hey, that's not very many of us. Okay, well, practice that. Y'all got 3 practice quizzes right here on the front. Don't forget, you got these 3 practice quizzes right here on the front page. It'll be some iteration of those. That's coming up on Wednesday. Oh, guys, don't make me put a bunch of 0 out of 10s in the grade book for your first grade of the semester. Y'all have A's right now. I don't want to see half the class go from A's to F's in week 2. All right, back to radicals. Back to radicals. Okay, you have learned how to rationalize, and for this first one, I'm going to show you the good old-fashioned way of rationalizing denominators. You've all learned that we can't have radicals on the bottom of a fraction or fractions inside of radicals, so we've got to deal with that, and the way that you've dealt with it in the past is you multiply it by a fancy version of 1, right? What would be your fancy version of 1 for this first problem? Root 2. Root 2 over root 2. Since we're multiplying by 1, we're not changing the value, just the format. The reason we do this is the denominator, when we do root 2 times root 2, that just gives us 2. And now we don't have a radical on the bottom anymore. Okay? And that's great. But I don't want you writing all that stuff down anymore. Okay? That's a multiply now. Because there's a faster way to do this. And I want you guys to be quick with this because you will be rationalizing. We'll probably do this like 500 times in this unit. You'll be rationalizing a lot of fractions in this unit. Okay, so it turns out that as long as a is not 0 or a negative number, when you go to divide by a square root of a or the square root of anything, so let's say I'm dividing by the square root of 7. Dividing by the square root of 7 is the equivalent to multiplying times root 7 over 7. Dividing by the square root of 5 is equivalent to multiplying by root 5 over 5. Dividing by the square root of 2 is equivalent to multiplying by root 2 over 2. So let me show you how I think through this. So when I see 4, I'm going to copy this 4 over here. When I see 4 divided by root 5, I think to myself, that would be way easier to do if instead of dividing by root 5, I just multiplied it times root 5 over 5. 4 divided by root 5 is the same as 4 times root 5 over 5. It just is. Dividing by root 5 is the same as multiplying by root 5 over 5. So my answer then is 4 root 5 over 5. And this piece right here, I'm going to put a little thought bubble around it because I wouldn't write this down. That's just what I'm thinking in my head. So same thing right here. I look at this and I see 2 divided by root 2. I think, yeah, fine. But that's really just 2 times root 2 over 2. And of course we would cancel those 2's and we would end up with just root 2, right? Dividing by root 2 is the same as multiplying by root 2 over 2. And then simplify to get our final answer of root 2. You guys getting this? Does it feel okay? So when I see 10 divided by root 6, I'm just going to think, oh, that's just 10 root 6 over 6. And then simplify. Simplify that 10 over 6, that would be 5 over 3. We'd still have a root 6 in the top. See if you can use that to simplify the rest of these in here. I'll give you a hint on the last one. I might actually simplify the root 18 before I do the changeover. Sometimes that works out a little easier. 12 divided by root 2 is the same as multiplied by root 2 over 2. Now, if you don't like this and you want to just do it the old-fashioned way where you multiply by a fancy version of 1, that's fine too. To me, this just saves me time. A lot of the times you're going to end up seeing fractions that have a root 2 or a root 3 on the bottom. And as long as you remember that dividing by root 2 is the same as multiplying root 2 over 2, that just makes it easier in my mind. It's up to you. Do you guys know why this works? X divided by root 2 is the same as x times 1 over root 2. Agreed? Dividing by a number is the same as multiplying by its reciprocal. Well, what's another way I could write 1 over root 2? If you multiply by a fancy version of 1 here, you're always going to end up getting the root on the top and just the number without a root on the bottom. And it doesn't matter whether this is a 2 or a 3, because if this is a 3, we'd be multiplying by root 3 over root 3, which is going to give us a 3 on the bottom and a root on. So it's always going to end up being the square root on the top and the whole number on the bottom. Does that make sense? Or here's another way of thinking about it. If we started here, x times root 2 over 2, and I did the reciprocal of root 2 over 2, that would be the same as x divided by 2 over root 2. And what's 2 divided by root 2? what would you multiply by root 2 to get 2? Root 2. 2 divided by root 2 is root 2. Anyways, it works. Use it if you like it. Ignore it if you don't. All right, SOHCAHTOA. We are not going to spend a whole lot of time on SOHCAHTOA, but let's just go over how it works. You got an angle theta, and let's assume it's a right triangle. So that means we've got a hypotenuse. We've got a side that's opposite the hypotenuse. We've got a side that's adjacent. Sorry, opposite the angle, a side that's adjacent to the angle. Does this all sound familiar to you? And so based on that, SOHCAHTOA tells us that the sine is equal to what over what? Give me some words. Opposite over hypotenuse. You guys have all done this 1,000 times, right? Back in geometry mostly. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Does that all sound familiar to you? Have you learned about the other 3 trig functions before? Did I ever teach you about secant and cosecant and cotangent? So this is cosecant. This is secant. And this is cotangent. These are often called the reciprocal trig functions because they are related to our main 3 trig functions, but they're reciprocals. So it turns out that cosecant is the reciprocal of sine. So cosecant is hypotenuse over opposite. Secant is the reciprocal of cosine. So it's hypotenuse over adjacent. And cotangent is the reciprocal of tangent, which is adjacent over opposite. So if you know sine, cosine, and tangent, finding secant, cosecant, and cotangent are really easily. You just have to flip stuff, but you got to know which goes with which. When I first started teaching this, and when I first learned it, I was like, it seems like they're setting us up for failure with this whole thing. Like, shouldn't secant go with sine and cosecant go with cosine? Wouldn't that make sense? Yeah, but they didn't do that. Why? Because they're trying to mess with us, man. They're trying to get us, but we're not going to fall for their tricks. We got it. We're going to just keep in mind. There is actually a geometric reason why sine goes with cosecant and cosine goes with secant. And if you really want to get into it, we can talk about it some other time. I'll be honest, I'm going to have to look it up again because I don't remember what it is off the top of my head. But there is a good reason why this is true, but we'll just remember. Cotangent goes with tangent. That's the easy one. The other two kind of flip-flop. Cosecant goes with sine. Secant goes with cosine. Okay? So easy peasy. So let's go ahead and draw ourselves a triangle. Now for right now, and you're going to see some of this in your assignment, they're going to give you an angle, and they're going to ask you to evaluate the sine, cosine, and tangent of that angle. The angle they gave us was pi over 3. Let's use our wondrous skills of angle awareness and write that in degrees. What would that be in degrees? Pi over 3. If you need to run it through a conversion by multiplying by a fancy version of 1, feel free to do that. You practice that a dozen times in your assignment. Some of you might have memorized what pi over 3 is in degrees. That would be wonderful. You're definitely going to want to have that at some point. Some of you might be thinking through, half circle is pi. So if I cut that into 3 equal pieces, how many degrees is each of those pieces? No matter which way you go, though, you're going to come up with the same answer, and that answer is how many degrees? 60 degrees. It is a 60-degree angle. So would you please draw me a triangle that's a right triangle and has a 60 degrees in it someplace? And when I do problems like this, I tend to draw a right triangle that looks kind of isosceles. And then I just put the angle wherever I want to. I'm going to say that that's the 60. All right. Ooh, that's a 30, 60, 90 triangle, isn't it? Hey, put some numbers on there for me. Get some numbers on there. Let's do the version without the fractions. You got them? Did you get them like really quick? Do they match mine? 1, 2, root 3. Are you guys starting to get good at remembering that the root 3 goes across from the 60 and the 1 goes across from the 30? No? Yes? Anybody else find any other tricks to help you out with that? Hypotenuse is 2. All right, well, go ahead and do sine, cosine, and tangent for me, please. The sine of pi over 3 would be the same as pi over, or the same as the sine of 60. You know sine is opposite over hypotenuse. If it helps you to label O, H, and A, go ahead and do that. You're not going to see me do that very much. But for some of us, it's been a while. You guys only spent a couple days on trig last year, is that right? Pretty quick reminder. But 2 years ago, I think we spent like a few weeks doing trig. You guys got pretty good at it, those of you who were in my class. Well, everybody, not just the people in my class, obviously. So sine was what? Root 3 over 2. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. We would probably just simplify that to root 3. Yeah. All right. Did you guys do your reciprocal functions already? I didn't leave you much room, but make sure that you are rationalizing those also. 2 over root 3. We're not going to leave it like that. We're going to change that to 2 root 3 over 3. Ooh, 1/2 is nice. The reciprocal of a half is just 2. Pi over 3 cotangent. We just flip that over. We get 1 over root 3, aka root 3 over 3. All right, so you'll have some problems in your textbook where they're going to ask you to evaluate some trig functions. I think each problem is only one of these. Okay, it'll be really quick. And the way you're going to do it is you're going to draw a triangle. I'll give you a hint. Those 3 problems, it's going to have, one of them's going to have a 30 in it, one's going to have a 45 in it, one's going to have a 60 in it. So you'll either be drawing a 30, 60, 90 triangle or a 45, 45, 90 triangle. Stick your numbers in there. Do your fraction, rationalize if you need to. We good? Yes, they also asked us to use a calculator to verify. So could you please get out your calculator and let's do sine. So I want you to type into your calculator the sine of pi over 3 and hit enter. And I want to make sure that everybody's getting the same answer on this one. It's going to be a decimal answer. It should be 0.8 something. Sine of pi over 3. Type that in just like I did. Hit enter. You should be getting 0.8. So it round to 0.9, but 0.866. Is that what your calculator is saying? There is no way that 100% of the people in this room are getting that same number out of their calculator. Who's getting something different? You guys are all getting the same answer? Yes? 2 people or not. Okay, awesome. Awesome. That's pretty lucky. That's the best ratio ever. It's usually about half and half. What do you suppose is the difference between the people who are getting 0.866 and the people who are getting something else? I'll give you a hint. Can you guys hit the mode button on your calculator really quickly? Hit the mode button there. And see if you can find a setting on your calculator that might explain why it's possible to get two different answers here. Anybody want to guess which setting it is? Are you finding it? The two of you who had something different, were you in degree mode? Did you figure out on yours how to switch it over to radian mode? Are you still rocking the Casio calculator? Do you get it? You got it? Oh, okay. Oh, I got you. There's probably a way to on my, like some of the ones I've seen, you have to hit second enter, and that'll give you a decimal approximation. You can try that. Yeah, so put it in radian mode if you haven't. All right, so let's make sure that's the correct answer. We got the square root of 3 divided by 2 is what our answer was. Oh, look, that's exactly the same. Nice. What else did they want us to check? Oh, they wanted to check secant. Can you go ahead and type in the secant of pi over 3? We're hoping our calculator spits out 2. Secant pi over 3. Do you see a secant button on your calculator anywhere? Don't look too hard. It's not there. There is no secant button on your calculator. If we can't do a secant, oh my goodness, then what are we going to do? Secant is related to which of the three main ones? Cosine, and it's the reciprocal. How do you do the reciprocal of something? You should do 1 divided by whatever it is, right? So do 1 over cosine pi over 3, and that'll be your secant. So our calculators do not have a secant button on it, but you can just do 1 divided by cosine of whatever your angle is, and that'll give you the secant. Okay. All right. We're running a little short on time here, so I'm going to speed this next part along. If I don't know the third side of a right triangle, I should have put a little box here. What tool do we have available to help us find that third side? Yes? Pythagoras' theorem. Invented by Sir Isaac Pythagoras. No, Pythagoras was around a long time before Sir Isaac anybody. No, it was invented by a member of the Pythagorean cult. That Pythagoras took credit for it. Guys, did you ever read about the Pythagorean cult? Your math teacher probably didn't talk too much about it because a lot of it's not suitable for school. Leave that to your own self-studies if you're interested. But they were into math and other things, and the math part, they did some pretty interesting geometry. Nobody knows for sure if Pythagoras invented the Pythagorean theorem, but it definitely came out of his cult. Let's see here. X is a leg, so that needs to go there. You guys know how to do Pythagorean theorem, right? Do we need to review this, or are we good? We're good, Mr. Height. Okay. $80 divides by 16, doesn't it? 16 times 5. Okay. All right, now we got 3 sides. We can go ahead and do our ratios. So go ahead and do your ratios there. So theta's up here, so we got to be careful. This is our opposite, hypotenuse and adjacent. Is that weird? A math cult? Does that seem strange to you guys? You know, the idea of like math and science being separated from religion is a pretty modern thing. Like you go back even like 150, 200 years ago, and like the biggest contributors to math and science were all deeply religious people. That's why they did what they did, was they were trying to understand like the nature of the universe and God better through math and science. So it's kind of a pretty interesting thing. And yeah, and in some cases, folks didn't like what they had to say. Like that Galileo. Was it Galileo? Who was the one that was... No, Copernicus was the one that was burned at the stake, wasn't he? Or excommunicated. I don't know if he was burned at the stake. Excommunicated for saying that the Earth revolved around the sun. It happens. Hey, there's something cool that somebody pointed out to me. This is several years ago. Do you guys remember back in geometry, we spent a lot of time talking about similar triangles and similar figures? And like there are some special conditions you could use to prove similar triangles. It was like SAS and SSS and AA, right? Remember all that? Fond memories, bad memories, whatever. They're memories. All memories are good memories. That's not true. Hey, I would like to introduce you to another triangle. So this triangle and this triangle must be similar triangles. Would you agree with me? Because this theta matches and this 90 degree matches. So AA, those two triangles are similar. Which means I can make these lengths any length that I want, as long as it's a multiple, like I use the same ratio to multiply these. When you look at 12 and 8 and 4 root 5, do you see a common factor in there? What's the common factor? 12, 8, and 4 root 5. 4 is a common factor, right? So I could multiply each of these sides by 1/4, and that would give me a similar triangle, agreed? So if I had thought about it before I started doing all this work here, I could have multiplied this by 1/4 and got 3. I could have multiplied this by 1/4, got root 5. Multiply this by 1/4 and got 2. I could have been dealing with those numbers instead of these numbers. And how would that have been helpful? I just wouldn't have had to reduce, right? I could have gone straight to root 5 over 3 for sine, 2 over 3 for cosine, and root 5 over 2 for tangent. It would have just, I could have done the reducing on the triangle up front rather than doing it 3 times with each of the things. Is that worth doing? I'll let you decide that. All right, let's finish up here. This last part here, I just want to review with you SOHCAHTOA. This is basically what I'm doing with my geometry students right now. We're going to take the entire week to do what I'm going to go over with you in about 5 minutes here. Okay, if you need more of an explanation, I'll be posting those videos I'll put them on our playlist. But let's just write SOHCAHTOA up here as a quick reminder. And I also want to remind you that when you write a trig equation, you are always going to have an angle and 2 sides. And the sides always go into the fraction, and the angle goes into the trig function. So I'm going to try and write an equation that has the values 37, 7, and x in it someplace. And it's going to be a SOHCAHTOA equation. And so what I need to do to start is figure out what's the x and the 7 in terms of opposite, adjacent, and hypotenuse. The 7 is definitely the hypotenuse, agreed? And the x is the opposite. So if I'm going to write an equation that contains all 3 of those values, the 7 and the 37 and the x, which equation am I going to have to use, sine, cosine, or tangent? We're going to have to use sine. That's the only one that includes both the opposite and the hypotenuse. Cosine, I don't have an adjacent. Tangent, I'm also missing an adjacent. This is going to have to be a sine equation. So I'm going to get it set up. Sine of something equals something over something. And then let's get all this stuff in the right place. Angle's 37. The angle goes inside the trig function. And sine is opposite over hypotenuse, so the x will go over the 7. Could you go through that process? Don't solve that just yet. Just go through that process for your other two triangles. Write me an equation. Just write me an equation. So 54. All right, do we remember how to solve these? Yeah, there's some tricks to them. So what I teach my geometry students is when x is in the fraction, turn the sine or the cosine of the tangent into a fraction and just cross multiply. Like that's the most straightforward way to do it. There are some shortcuts. For example, if x is in the top, you can solve for x by just multiplying by what's in the bottom. So x would equal 7 times whatever the sine of 37 is. And I'm going to go ahead and type that into my calculator. Oh, what should I make sure to do before I type this into my calculator? No. Mode. Think mode. What mode should we be in? Radian or degree? Go ahead and switch into degree mode. Degree mode. The mode button's up at the top of your calculator. If you do these problems and you're still in radian mode, you're going to get wrong answers for all of them. That's something you need to become very conscious of because we will be flipping back and forth degree mode and radian mode consistently throughout the rest of the unit. Well, the rest of the year, really. So anytime you hit a sine, a cosine, or a tangent, or an inverse of any of those things, you need to make sure you're in the right mode. The shortcut for when x is in the bottom of your fraction, I think this is the one that you mentioned a minute ago. That's when you can flip-flop the x and the trig function. These are all just shortcuts. However you want to do them is fine. Honestly, when you're doing a problem like this in an assignment or in a test, I need to see your original equation, and then you can jump straight to the answer from there. I don't need to see steps in between. That's about 5.10. And then when the variable's locked up inside of your trig function, what do we do there? There's a couple ways for us to think about it. One of them is how many people learned it this way? You change your tangent to an inverse tangent. What happens when we switch from a function to its inverse? What happens to our inputs and outputs? This is the big concept from first semester. They flip, right? Inputs become outputs, outputs become inputs. So this was our output, it becomes our input. And theta was our input, it becomes our output, and now we can type that into our calculator. Make sure you put units on that. That's 22.42 degrees. All right. We made a change first period. You guys want to go with the change that first period made? Instead of doing 4 problems here, we changed it to 2 problems. You guys want to do that? Okay. And I'll even start you off on the first one, okay? So we're going to get rid of 1 through 7 odd. Now I need you guys to stick with me until you see how to do this. This is kind of like what we're going to actually be focusing on Wednesday. I figured this will be a little bit easier. So I'm going to go through and I'm going to show you. So getting rid of 1 through 7 odd, turning it into just 9. No, sorry. I'm on the wrong page. 4.2. 9 and 11. So 4 problems down to 2. And I'm going to show you how to do number 9. Okay, you need to write this down quickly though, because we're very quickly running out of time. You guys with me here still? Write this down, number 9. And then if you're putting this in your notes and copying it over later, that's fine. What they tell you in number 9 is that the sine of theta equals 3 over 7. Your job is to write the other 6 trig functions, the cosine of theta, the tangent of theta, the secant of theta, the cosecant of theta, and the cotangent of theta. That's going to be your answer. How in the heck are we going to do that? Well, let me show you. You ready? Do you see how I got that 3 over 7? Do you see where I got the 3 and the 7 from? Because sine is opposite over hypotenuse. I put it in opposite and hypotenuse. Now, we're going to need to know this side, too. How do you suppose we're going to find that? Good old Pythagoras. So we'll do 3 squared plus x squared equals 7 squared. And then we'll solve that. 9 plus x squared is 49. Minus 9 on both sides gets us 40. Take a square root on both sides gets us 2 root 10. Do you feel like you have everything you need now to complete that problem? All right, so we'll make that trade. Everything else that you're going to do is very similar to a problem on the first page of our notes, okay? I do need you to complete these 10 problems up above as well. Just make sure you got lots of practice with the right triangle stuff. This is going to be the last time that we practice right triangle trig, but it will come up again and again and again, okay? So make sure that we... I'll check your assignments on Wednesday.